This video gives a quick overview of a paper presented at the NeurIPS conference 2019. Planning under uncertainty in MDPs can be captured using a dynamic Bayesian network that shows the evolution of states over time from left to right, conditioned on actions. The goal is to find an assignment to action, the orange nodes, that maximizes the expected cumulative reward, represented by the R node on the bottom right. Here it is assumed that the agent knows the state when choosing the next action. In partially observable MDPs, the agent does not know the state, but instead has partial observations revealing some information as shown at the bottom. In both images, we emphasize that states, actions, and observations are described by sets of variables, so they all have exponentially many possible values. Planning in such factored POMDPs is computationally hard. Our main contribution is a new algorithm, SNAP, that tackles such problems. It is an approximate solver, suboptimal even when it has enough time, but very effective on large problems where other algorithms are too slow. SNAP uses the idea of aggregate simulation, which was developed for MDP planning with the SOGBOFA system. SOGBOFA takes as input and symbolic representation of the domain model, as in this example taken from a recent planning competition, or the toy problem on the top left of this slide. SOGBOFA translates the model to a computation graph as shown on the right, where action variables, the orange nodes, are symbolic inputs, and one node represents an approximation of the cumulative reward. SOGBOFA then optimizes action variables using automatic differentiation. The forward computation was shown to be equivalent to belief propagation with no downstream evidence, which means information only flows forward in the SOGBOFA graph and no backward messages are used in BP. This fact is crucial for the SOGBOFA construction. Unfortunately, this breaks down for POMDPs because observation nodes shown at the bottom are downstream from actions and they serve as evidence. Our solution is to reorder the computations by enumerating possible values for observations and conditioning on these values. This works when there are only a few values. In this example, we have only two values, and we generate two tracks in the graph. The graph computes probabilities, belief states, and POMDP values. The last portion computes the value of a belief state by using the SOGBOFA construction on the nodes representing the belief stage in the graph. When there are many observation values, we sample a few. The challenge is that we must generate a value at construction time, which is sampled conditioned on the action, which is only known during optimization time. Sampling networks achieve this and generate both the value and a node in the graph that calculates its probability to be used in other portions. And this is embedded in the large construction. Optimization of action proceeds using automatic differentiation and gradient search. Experiments in the paper show that SNAP has excellent performance on a range of challenge problems with large state, action, and observation spaces. Please see the paper for more details on the algorithm and experiments.